you want an introduction?
No.
Okay, there you go.
Okay.
Sergio.
Sergio. My name is Sergio Davis. I'm from the University of Manchester, from the Advanced Processor Technology Group. Spinnaker is the project on which I'm working. Now is part of the Human Brain Project. So what I'm gonna say today is something about the architecture and how we use it for neural network simulation. So we cover the principle of these architectures, the architecture itself, the design, and then we'll go to the challenges that we're facing doing our research, developing this project. A few examples then, and a few considerations at the end. Well, first of all, Spinnaker is an acronym. Stands for Spiking Neural Network Architectures, provided that you say it enough quickly and you and you exchange a few letters here and there. So, spiking neural network architecture, and is used for real-time simulation of this kind of neural network. And it's a computing platform, so inside this you can find off-the-shelf CPUs and a bit of interconnection there, a bit of technology which we developed in-house, which allows this network actually to communicate, to work as biological neural network does. And then, as I said, all the architecture has been inspired from biology. But what does this mean? So, how can a massively parallel architecture allow us to understand how things work? So, if we pick up biology, there are a lot of descriptions or theories about how pieces of the brain should work. For example, cortex models. Yes, microcortical column. Now I can say it. Microcortical models, which are described somehow from the biology, but there aren't actually computers enough powerful to simulate all this and try to understand if this model is either good or bad or somewhere in between these two. Or on the other side, if we want to see the things in a different perspective, how can the biology improve our technology in computing? So, if we have a neural network which is able also to not self-heal, but work around problems, so being fault tolerant, how can we exploit this into computers to make this technology work, even if there are parts not working? Okay. Building brains. So let's start from the biological neural networks. Let's pick up one which we carry always with us most of the time. Sometimes we leave it on the in the bed, but let's say that inside this 2-liter thing that we bring with us, we have something in the order of 100 billion neurons. For this small number here actually means about approximately 100 billion neurons, and this incredible amount of synapses which interconnects these neurons. Each neuron is actually a very, very simple unit, does a very, very simple computation. We have it described by some neuroscientists. We have the complete model, the Hodgkin-Huxley model, but then we have also simplified models if we go down to leak, integrate, and fire models. So, we know neurons, how they work. There has been they have been thoroughly studied. And the bit which we are struggling with is this connectivity. This amount of synapses is actually creating some troubles to understand fully. But nonetheless, think about, we were discussing just before with Chris, how much does a workstation consume, computer? Let's say between 200 and 400 watt, depending on the workstation. Now, you know how much our brain consumes?
One electric bulb.
About?
One electric bulb.
Modern one or an old one?
Yeah, well, I think it's about 40 or
20 watt, about.
20 watts, yeah.
Yeah, it's about 20 watts. So we are one order of magnitude lower than today's computer. And still, those computers are not able to do what the brain does. Even if the units are very, very simple and very well known.
So it must implement reversal computation.
Yeah, that's the point. Using the computer to try and understand how this works. We know that neurons are very low performance components, so they are very slow, they are very relaxed, and the communication between them is both low speed and unreliable. But still, we are going for something incredibly fast, incredibly reliable, but all what we need for this is something very slow and even unreliable. It's okay. Adaptivity tolerant, well, we were talking about before about the fault tolerance. The brain is self-rewiring, works around faults most of the times. And most important, if you're able to read a book, you're also able sometimes to remember it. Okay. And all this now, if we want to start moving towards a computing architecture, let's start describing. So, let's take the example of the microcortical column. This microcortical column, as it has been proposed by some authors, has a regular instruction which is then being repeated around in a lot of copies, where each neuron has a lot of inputs and has a single output. It's like a gate, a logic gate. Who is from the electronic side of computing and who is from the software side of computing? Hardware? Who works with the hardware? Yeah. None of us. No. Okay, so it's all on. Okay.
If software only gets half of it.
No, it's fine. Just to understand. So, logic gates have a lot of input and one output, generally. And this is how neurons work. And you can repeat this discussion over multiple scales. You can have a single cortical column or you can have a large array. Each of them performs a simple computation. Then you put all this together and you have something wonderful. So there is some regularity in this brain structure. Okay. And then we come to this architecture which actually we are building to reproduce a biological neural network. This is basically a computing architecture. Each of these green nodes is a spinnaker node which hosts a lot of cores, and with all this interconnected, we'll see how, we aim to replicate about 1% of the human brain neuron count, so approximately 1 billion neurons.
So is this a KRE2 cube?
Sorry, is?
This architecture is KRE2 cube.
KRE2 cube, I don't know this.
It's, okay. Just the graphical structure here.
Yeah.
The name for this structure.
Torus. Yes, it's a torus,
yeah,
and where each of these nodes is connected with the other 6 neighbors.
So actually that's in fact the picture of the architecture. So each
Yes.
node is a computer, or is it a processor containing
It's
multiple neurons? Or
exactly. It's a computing multiprocessor. So it's a chip multiprocessor. It's a single chip which has 18. Let's see. No, it'll come later. Each of these has 18 cores within. Very simple. So something that you can find in your mobile phone, for example. Something which is low power.
So I was just wondering if there was
Yes.
a particular motivation for it being a two-dimensional surface. I mean, so I guess you could get six-way connectivity without
And you can
that.
get also the three-dimensional cube. Sure.
Yeah.
It's just an arbitrary choice.
Okay.
But this choice was made in such a way that there is always a path which goes to the chips, to all the chips inside the machine. So, if for example one packet gets lost, for sure will hit at some point the core on which it should have.
I mean, a number of supercomputers have this architecture.
Yeah.
And you can prove stuff like it has lots of Hamilton cycles in it.
Okay.
So if you violate one, you have lots of
So this is actually just a virtual topology. If you see the physical topology, you don't see anything else than the racks of cabinets and cabinets of boards, where each of these chip is mounted. But we'll go through that.
But actually now I see it, it's got these diagonals on it
Yes.
that I wasn't quite expecting. So they're slightly different from...
Yes, there is not only the X and Y, but there is also one diagonal. We'll go through this. So, the idea is that the network, which you were focusing on before, is actually only a virtualized topology, communication channels. Then you can decide where to route the packets. Then each core, each chip actually has its own time, meaning has its own clock. They don't have a general clock which keeps track of time around itself. We say time models itself because the time at which an event arrives is the time at which an event arrives. The event arrives. There is no timestamp associated with the event apart from the time at which it arrives. Energy frugality, because the real if you pick up a computer, what you pay is not only the cost of the processor itself, but the cost actually to perform the computation. So there is a one-off which is the cost of the processor, but they are off the shelf, so they are pretty cheap. But if you start running it for a very long time, then that becomes the major issue. Okay? And we know that here we don't consume a lot of power. So going towards that direction, we go for some energy frugality, and it's a trade-off against the computational power that we can afford in these computers, in this system. So going through the architecture, this is a block model of one of the chips. Here there are 18 cores. These 18 cores have one router in common, which is shared, and connects each router with each core with every other core inside the chip, plus the 6 links for the neighbor chips. On the other side, you can see some memory and an Ethernet connection. That's the way that we communicate with the machine. Intrinsic parallelism, because we have a lot of cores, each does its own computation. Asynchronous code execution, because each core works based on events. It's asynchronous, meaning that you don't control the flow of the execution, but you just control how to handle each single event that arrives to each of the cores. The memory is shared between the cores, but each of them can access it independently, so it's incoherent memory. And since all this is all digital, it's just configurable on the fly, you can just reroute around problems, for example, on the fly reconfiguration. Here you can see this is actually the die of the chip. The 18 cores, one here and one here. But you can see that the most of the surface of this die is actually memory. So if this is the area of the core, these are 3 banks of memory which are attached to each core.
So this means each core has its own memory.
Yes, there is a portion of memory which is attached to the core. It's a tightly coupled memory.
But
It's
can
called.
other write to and read from other memory? Can each?
No.
So they're
No.
independent.
They are independent, at least for this. But if you go then to the SD-ROM,
Okay.
each of them can write on or read from the entire memory. Okay.
And where is SD-RAM?
It's actually mounted on the top. It's glued on the top,
Okay.
and there are stitch bonds that goes from one to the other.
How big is it?
128 megabytes.
Okay. That used to be a lot.
Sorry?
That used to be a lot.
Some time ago, yes. But for what we do, actually, is more than enough. We never really encountered any particular issue with this amount at the moment. So, 2 dies in a single chip. Here in between, you can see the router, which is actually shared between all of them and allows packets to travel around and outside. SD-RAM, and here, this is the content of the routing table within the chip itself. If you see, most of this is just memory. These are 96 kilobytes of memory for each of the cores. Not very much, but good for what we do.
So it's like in the brain, most of the stuff is synapses.
Yeah. Yeah.
Which is,
Not only, but if you think, each neuron only knows what happens around itself. One neuron doesn't know what happens to another neuron on the other side. So there shouldn't be any need for one neuron to know what happens to the other neuron far away. Okay? And then you combine all these chips in a nice 2D grid, and you see the 6 links here, horizontal, vertical, and just one of the 2 diagonals. And you increase the scale of this. Well, and then you mount them first, and you have, we classify them by the number of cores that are available. So for example, this board has 4 chips equivalent to 72 cores. So we say it's a 10 to the power 2 machine, 102 machine, 100 cores approximately. Okay. Connected as we saw before. And this actually can be powered from a USB. I used to power it from the USB generally.
will you explain why did you use 6 links rather than, let's say, 4?
Yes, I can, but this goes into the hardware. So we had a package which we had to fit in with, if I remember correctly, 300 BGA. It's a 300 BGA package. If you do the count of all the power lines, all the memory lines, all the I/O lines, you end up that only 6 links could be made with that amount of balls of I/Os. Okay. Yes.
So that's why you got the 6 because of this
Limitation.
You could also then have had the 3-ary end cube. You would go up the dimension there and then you'd get 6.
Sorry? I don't understand.
Sorry, I'll ask you later.
Okay. and then you scale up. And this is the basic building block for the final machine, where you have 48 chips plus some logic here, FPGAs, to allow inter-board connections. Now you see them in a nice squared way, but if you draw logically, it's more like an hexagon. Still, you can see the 2D grid with just one diagonal. It's still there. That doesn't change. Then you pick up 3 of these. Sorry. Okay. Yes, you pick up 3 of these. You do the appropriate graphical modification, and you will see that these 3 hexagons actually are equivalent to 12 by 12 square. So if you pick up this side here and you put it there, and you pick up this side here and put it up there, you end up with a 12 by 12 squared system.
So is it strictly 1 neuron per core?
No, no, I'm not yet there.
Right.
Just one moment. It's not much more. So this is the 3-board system, which is the minimal unit with multiple boards. And you scale up to 24 of these. This is still a portable system. It weighs 40 kilos and you need 2 persons to carry it in the trunk of a car, but still is portable.
I once carried a synthesizer, solid synthesizer by myself, which was 40 kilos.
Yeah, 40 kilos is one person, I think.
But it was very
Right for
hard.
the back loads.
It's not very comfortable to bring it, to carry it with you.
It is heavy, yeah.
And then you pack 5 of them into a single cabinet and you wire them. So this has been done actually by one of our PhD students.
I love this movie.
You know this movie? So, it's a time lapse.
Oh, it's only
Steve
students who are
Ferber.
Steve Faber is the head of the group.
Right.
Do you know him?
Well, this my former supervisor has a grant with him working on these interconnection architectures, which
Who
is
is your
it's Ian Stewart. Ian Stewart.
Ian Stewart?
Chris has a grant with him as well.
Oh, with Ferber.
Yeah. Well, no, not the. It's partly isn't funded by the
Human Brain
Brain Project.
So, how many cups of coffee did he get through?
4 hours. It's 4 hours that took to do all this.
Did you see me stop and had a break, had a cup of coffee?
Actually, here they seem pretty random, but actually there is this regularity in all these cables, and this confusion is given by the fact that those cables cannot be longer than 1 meter. You know, SATA cables have a limited length, so you have to interleave those boards so that the system exactly cannot just do the tour around, but actually needs to be interleaved.
It is a lot of connections to get it right.
Sorry?
It is a lot of connections to get it right.
That's right, yeah.
If,
Is it obvious at the end to test that you got it right?
No, well, this, if you see during this video, I'll show you. Actually, there is this computer. Yeah, you can see that he has always a computer on the side, which is connected to this, and actually, automatically, every time you put the SATA cable up, the computer checks that the SATA cable is connected properly between the correct nodes and between the correct ports. Because if you see the board itself, if you see the board here, you have 6 SATA links on one side and 3 on the other. So this will be used only for I/O. But these 6 here are for the interconnection with the other boards.
But does it matter if you get the wrong cable? I mean, in the brain it doesn't matter. The synapses still connect. So why maybe it brings an
Because
advantage
this is
if you-
still the the real network of chips. So what you count them 0, 1, 2, 3, 4, then you should have 5, 6, 7, 8. What happens if you start having 100, 100, 101, 102? The system will not really understand what's doing.
But do you ever test this? Once you've built it, do you ever test it by just unplugging and seeing if it reroutes correctly?
I don't think that Johnny would agree to
Okay,
that.
okay.
And then you pick up 10 of these cabinets, put them in a computer data center, and you have, well, one cabinet is one mouse brain. If you pick up 10 cabinets, you have 10 mice. Or a rat. or something like a rat, yes. But if we talk about power consumption, one single 48 node board consumes between 75 90 watts, so depending on the load that you put on it. But if you pick up a 104 machine, so one rack, it goes up to 1.5 kilowatts, which is still okay because you can still power it from a general socket. You don't need anything special. You start to need something special for if you go for a cabinet. Or if you go for 10 cabinet, then this starts to become an interesting challenge. Okay. Again, challenges. What the challenges that we are facing during this project. First is a mapping problem. So we have this network, which we describe as a graph, where nodes are actually populations of neurons, and the edges are synapses, if you want to see them that way. Each population can be made up of 256 neurons for the moment, but in the longer run we aim to achieve 1,000 neurons. And you can put one population per core.
So 256 per core, and you have 18 cores.
Yes, in a chip. Actually, of these 18 cores, one is used to keep control over the entire network of chips. So it's a root core, is called. And another one is used as a spare. So we don't accept only chips which have all the 18 cores working, but we accept also those who have 17.
So 16.
16 is what we use for neural networks simulation. Plus 1, which we may use even during the simulation if one core goes badly. Okay? So, we start from this graph, and there are two things which happen. First is the description of the model itself. So, what type of neurons are we trying to simulate? And Hutchin-Huxley, a leak, integrate, and fire. So, here there is a bit of C development that describes the model, how to perform the integration, and so on. And on the other side, there is the description of the network. So, from the network, you extract, from the graph, you extract the connection between the various nodes, and you populate the routing table. Okay, easy. What happens at this point is that each model doesn't know who it is connected. It only happens, this connection happens only in the moment one neuron fires or one network packet is emitted. Then this packet goes to the router, and the router at that point looks in the routing table and propagates it where is appropriate.
So is the virtualization total in the sense that there are no constraints on the topology of the final network given the physical topology? It's completely virtualized.
Yeah. It's detached. The two things are detached.
But does it favour certain kinds of topologies, simply that they could be more
There are-
efficiently packed?
Okay, there are limitations because the routing table, the number of entries in the routing table is finite.
Yeah.
But if you abstract over this, it's not a problem. So, you have a population of neurons, and you map each of these to one particular core in the network. So we have now a problem with the networking. We have that each neuron connects to 1,000 of others. How the router is able to cope with this?
So you say
Oops,
that
sorry.
each neuron there it has 1,000 inputs.
Each neuron projects his spikes to another 1,000 neurons.
Okay.
Each neuron can collect spikes from, I don't know, 10,000, 1,000, 10,000. It's in that order of magnitude.
Bidirect links or
Synapses, yes, point to point.
so each
well,
can have
There is an axon. From the axon, there are interconnection with synapses with the dendrites of other neurons. So it's not a point to point, but is from one stripe, from one output to multiple inputs.
but sorry, what is the constraint on the number of synapses of each neuron? How many synapses each neuron can have in this connector?
Okay. There are numbers for that we worked out. But the constraint is on the fan-in rather than the fan-out. So one neuron communicates this spike, this packet, to a set of other cores, and this doesn't have any particular limitation apart from the number of entries. Okay, the number of entries in the routing table. But one packet can hypothetically go to all the cores in the machine. There is no problem with that. Then, when the packet is received, there is some processing power that is required to propagate that spike to the appropriate neurons inside that particular core.
Is that biologically representative, that imbalance between inputs and outputs? It's the architecture.
What?
I was just wondering if that was biologically representative of people
Those
bringing it
numbers, the 1,000 of...
No, I just mean the relative imbalance, the restrictions on the input versus the outputs, synaptic connection. I mean, is the human brain simply limited in terms of
Well,
outbound connectivity rather than inbound connectivity?
those figures were taken out of biological numbers.
Okay.
Now, I don't know to which part of the brain they were referring to when they thought about those, but biologically inspired, let's say.
I actually have a paper and I did combinatorial analysis exactly on these things,
Okay.
on the output bounds, and actually the relation is that usually in fact it's very close, the output connectivity and input is. If it's close, then it's good.
But if you think in the brain there is a big variability depending on the areas,
Yes.
on the number of the fan-in compared with the fan-out. So if
I was talking about average, but indeed,
Yeah.
yes.
there is a
Motor neurons
variation.
have about 30,000 synapses when the sensor can have just one or two.
Exactly. So for orders of magnitude, yeah, okay, you can do an average, but is it really meaningful?
It is. So, in some sense.
In some sense, yes. Okay. So, how does the network work? Each packet, which represents a single spike. Inside, there is an event ID, which represents the source of the spike. So each neuron has an identifier, and the packet are source routed. There are 4 types of packet which are routed by the Spinnaker router: multicast, point-to-point, nearest neighbor, and the fixed route. Multicast are the one that actually carry spikes. Point-to-point are used for communication loading, data loading programs. Nearest neighbor are used to check that actually everything is working also on the entire system. And the fixed route are used for debugging. So, since the packet goes out always following a particular route, you can use the entire space just to provide data. I won't go much more into these details, but this is the interesting bit related to the router. If you pick up one distribution tree, you start from one point, and you know that you need to end up, for example, here and here, or 1, 2, and 3. The same packet is then emitted from here, goes through various routers, and arrives here, the first one. The first one says, so, I need to propagate it to those 2 cores, or 3 cores, or 1 core, whatever, and to those output link. This is possible because in the routing table, the routing entry specifies to which core the packet needs to go and to which link it needs to go, and is propagated at the same time. So one single clock sends it to all the cores and all the links which are marked. How do we select the routing entry? Starting from the key. This key, which is the identifier of the neuron which fired, may have a match into this ternary CAM. So you have a portion of the key which refers to the population ID, the population ID, and then inside that population you have a specific neuron ID. So you match the population, and you know that any spike coming from that particular population goes down to that particular core or that particular link. Okay? So, now that we went through all this challenge at least in the description of the challenge of the configuration of the machine, we have just one model that does the job for one set of software, one set of tools. We call it the tool chain, that actually starts from the description of neural networks in Pine, if you know the language, and goes down